In this lesson, we'll show that every prime number has a primitive root, and we will use primitive roots to solve congruences. So we will now prove that every prime number has a primitive root. For every prime p, there exist primitive roots mod p. Let's look at the reduced residue system 1, 2, 3 up to p minus 1 mod p. So each of these residues in this reduced residue system mod p has an order mod p, since they're all relatively prime to p, and so we know that the order of each of these elements divides p minus 1. I'm going to define capital N of h to be the number of integers whose order is h. So let capital N of h be a counting number, so it's going to be the number of the elements in this reduced residue system. So it's the number of these integers whose order mod p is h. So capital N of h is the number of these residues with order h. So we know that if the order of an element, say A, mod p is h, then h divides phi of p, which is p minus 1. Okay, so we know that all the orders divide p minus 1. We also know that every element of this reduced residue system has some order, because they're all relatively prime to p. So also, every element of this reduced residue system has an order mod p. So therefore, if I add up all the capital N's for all the possible orders, we'll see that that will partition this reduced residue system. Another way of writing this is, therefore, we have that if I add up, so I have capital sigma, and I'm going to add up all these counts. So remember, capital N of h counts the number of residues with order h. If I add up all these N of h for all h dividing p minus 1, then that should equal all of this reduced residue system. So I've counted every single element of this reduced residue system exactly once in with these capital N's. So the total should equal p minus 1. because there's p-1 elements in this reduced residue system. So what we're going to show is that capital N of H actually equals phi of H for each H dividing p-1. But first we'll show that it either equals 0 or equals phi of H. So we will show that for each H dividing p-1, capital N of H equals 0 or capital N of H equals phi of H, the Euler phi function of H. Well, clearly if no element of this reduced residue system has order H, then N of H is equal to 0. So if no integer has order H, then capital N of H equals 0. So now let's suppose that there's some element that's called A that has order H. So if the order of some element A is H, then we're going to show that capital N of H must be phi of H. But in order to do that, we're going to look at the congruence x to the power H is congruent to 1 mod P. So then consider the congruence x to the power H is congruent to 1 mod P. So this is a polynomial congruence, and although we haven't shown it yet, we will prove this in later lectures, that a polynomial congruence with degree H can have at most H mutually incongruent solutions. So this is a polynomial congruence of degree H, because we have x to the power H, and therefore it can have at most H mutually incongruent solutions. This is similar to the fundamental theorem of algebra, which states that a polynomial of degree H can have at most H distinct roots. This polynomial congruence has at most H mutually incongruent solutions. But consider A raised to the powers 1, 2, 3, all the way up to H. But A squared, A cubed, up to A to the power H are all solutions of this congruence, and they're all mutually incongruent. These are all mutually incongruent solutions of this congruence. is if I raise any one of these numbers to the power h, that will definitely be congruent to 1 mod p. And each one of these is incongruent because h is the order of a. So this polynomial congruence has at most h mutually incongruent solutions. I've just demonstrated that there's h of them right here, so there must be exactly h solutions. So there are exactly h solutions to this congruence. Since there's exactly h solutions, any solution to this congruence must be congruent to one of these powers of a. So any solution of this congruence must be congruent to a to some power r for some r. So we showed earlier in a previous lecture that the order of a to the power r mod p is the order of a, which is h, divided by the greatest common divisor of r and h. So when is it possible for the order of a to the r to equal h? Well, that's only true, the order of a to the r equals h, exactly when the denominator, greatest common divisor of r and h, equals 1. So the order of a to the r mod p equals h if and only if the greatest common divisor of r and h is equal to 1. So the order of a to the r equals h exactly when r is relatively prime to h. So how many of the exponents 1 through h are relatively prime to h? Well, there's exactly phi of h of them. So therefore, among the numbers a squared, a cubed, all the way up to ah, there are exactly phi of h of these numbers that have order h. So if a has order h, then we've just shown that the number of residues that have order h must equal phi of h. So we've just shown that for any order h, capital N of h either equals 0 or equals phi of h. So we've just shown that capital N of h is always less than or equal to phi of h. for each h dividing p minus 1, capital N of h is less than or equal to phi of h. Now we'll need to use another fact about the Euler phi function that we will prove later. Only fact about the Euler phi function. That we will prove later. The fact is, if you take the sum of phi of all the divisors of an integer n, so take phi of d, where d divides n, so you sum up all of the phi of d, where d is a divisor of n, this will equal n. So that is the sum of the values of the phi function taken over all divisors of n that will equal n. Okay, so we're going to use this fact. Now we showed that capital N of h is less than or equal to phi of h. So suppose there's one particular h dividing p minus 1 where n of h is less than phi of h. So now suppose there is an h dividing p minus 1 with capital N of h, so the number of residues with order h, strictly less than phi of h. Then recall earlier we showed that p minus 1 equals the sum over all of h dividing p minus 1 of these capital N of h. And if one of these capital N of h is strictly less than phi of h, then this sum will be strictly less than the sum of phi of h, where h divides p minus 1. But by this fact that I quoted above, this will equal p minus 1. So we see we get a contradiction. If there was an h where capital N of h was less than phi of h, then p minus 1 would be less than p minus 1, which is a contradiction. Therefore, capital N of h always equals phi of h for each h dividing p minus 1. But p minus 1 divides p minus 1. So capital N of p minus 1 equals phi of p minus 1. In other words, there are phi of p minus 1 residues who have order p minus 1. But an integer with order p minus 1 is by definition a primitive root, mod p. So then there are phi of p minus 1 integers with order p minus 1 mod p, but all these integers are therefore primitive roots. Thus, there are phi of p minus 1 primitive roots mod p. So not only have we shown that for every prime number there are primitive roots mod p, we actually know how many there are. There's phi of p minus 1 primitive roots mod p for any prime p. So I'd like to summarize some facts we know about primitive roots mod a prime number. So if a is a primitive root mod p, then 1, we know that the order of a mod p is phi of p, which is p minus 1. Secondly, if I take the powers of a mod p, then I can generate a reduced residue system mod p. So a squared, a cubed, up to a to the power p minus 1, this will equal a reduced residue system mod p. So this set is congruent to the reduced residue system 1, 2, 3, up to p minus 1. So we're going to use this fact to solve congruences in a bit. But first I'm going to prove another theorem. For p prime, let a be a primitive root mod p. Okay, so we're guaranteed from the previous theorem, we know that there is a primitive root mod p, so let a be a primitive root mod p. There's a couple of theorems here. A to the power k is congruent to 1 mod p if and only if k is congruent to 0 mod p minus 1. And then an extension of this theorem, a to the k is congruent to a to the n mod p if and only if k is congruent to n mod p minus 1. So we'll use these theorems to prove congruences. So let's first prove statement 1. This is an if and only if statement, so I want to prove the forward implication. So I want to assume that a to the k is congruent to 1 mod p. Since the order of a is p minus 1, because a is a primitive root. We see that a to the k being congruent to 1 implies that p minus 1 divides k. Then k must be congruent to 0 mod p minus 1. Conversely, suppose k is congruent to 0 mod p minus 1. And k equals m times p minus 1 for some integer m. Then a to the k equals a to the m times p minus 1. And we know a to the p minus 1, or a to the m power, will be just congruent to 1 because a to the p minus 1 is congruent to 1 mod p. So that finishes the proof of 1. So I need the proof of 1 to prove the proof of 2. So let's start off by assuming that a to the k is congruent to a to the n. Suppose a to the k is congruent to a to the n. Then, without loss of generality, let's assume k is greater than or equal to n. Without loss of generality, let's assume k is greater than or equal to n. Then, by dividing both sides by a to the n, we have that a to the k minus n is congruent to 1 mod p. But by 1, we've shown that that means that k minus n is congruent to 0 mod p minus 1. K minus n is congruent to 0 mod p minus 1, and therefore k is congruent to n. Mod p minus 1. For the reverse implication, suppose k is congruent to n. Mod p minus 1. Then k minus n is congruent to 0 mod p minus 1. Again, using the first part by 1, a to the k minus n is therefore congruent to 1 mod p. And then multiplying both sides by a to the n, gives us a to the k congruent to a to the n mod p. So let's look back at these theorems. What this tells me is that I can use primitive roots to solve congruences by rewriting things in terms of a power of a primitive root And then I can solve a congruence in the exponents. And if I can solve a congruence in the exponents, that will help me solve a congruence, solve the original congruence mod p. Let me show you an example of this. So let's solve a congruence like 7x cubed is congruent to 4 mod 13. So I need a primitive root mod 13. We've already shown that 2 is a primitive root mod 13. And the powers of 2 form a reduced residue system mod 13. So let's look at the residues of powers of 2 mod 13 again. So I've written the powers of 2 up from 2 to the first power up to 2 to the 12th power, and below it I've written its residue mod 13. So what I'm going to do is write every factor of the above congruence as a power of 2, and then I'm going to solve an easier congruence in the exponents. In the exponents, we'll just have a linear congruence. And we'll use the previous theorem. So we just showed that 2 to the k is congruent to 2 to the n mod 13 if and only if k is congruent to n mod 12. So we can solve this congruence by replacing all the factors in this congruence as powers of 2 and solving a congruence in the exponent. So we can replace each factor by a power of 2 and solve an easier congruence in the exponents. But when we solve it in the exponents, we'll be working mod 12. So then our congruent 7x cubed congruent to 4 mod 13. I can rewrite 7 as 2 to the power 11. So 7 is congruent to 2 to the power 11. And x, I'm going to rewrite x as 2 to the power y. So we don't know which residue is congruent to x. So I'm going to write it as 2 to the power y. So 2 to the power y cubed. And 4 I'm going to replace with its power of 2, which is 2 squared. Then this becomes, on the left-hand side, 2 to the power 3y plus 11 is congruent to 2 squared mod 13. But this congruence is equivalent to 3y plus 11 is congruent to 2 mod 12. So if I solve this congruence, then I can plug y back in and solve for x in the original congruence. So let's solve 3y plus 11 is congruent to 2 mod 12. If I subtract 11 from both sides, I get that 3y is congruent to negative 9 mod 12. And I can divide everything by 3, so y is congruent to negative 3. And I have to reduce the modulus by dividing by 3 as well. So y is congruent to negative 3 mod 4. So y is congruent to 1 mod 4. So when I'm solving my congruence mod 12, y will be congruent to 1 mod 12. And if I add 4 to that, that'll be also congruent to 5 mod 12. And adding 4 again, I get that y is congruent to 9 mod 12 as well. So if y is congruent to 1, 5, or 9 mod 12, then x, which I rewrote as 2 to the power of y, will be congruent to 2 to the power 1, 2 to the power 5, or 2 to the power 9 mod 13. And looking up at the table, we see that x is therefore congruent to 2. 2 to the 5th would be 6, and 2 to the 9th would be 5 mod 13. So we're using the fact that the powers of a primitive root generate a reduced residue system mod of prime, so we can rewrite every residue as a power of 2 and solve the congruence in the exponent instead of solving a more complicated congruence like this cubic polynomial congruence.